if you are building AI video generators, you already know the single biggest headache in the field right now. It's like by far.
Oh, yeah. 3D spatial consistency.
Exactly. 3D spatial consistency. You prompt a model to, pan the camera across a room, look at a doorway, and then pan back. And by the time the camera returns, that doorway gets mutated into a window. The wallpaper has completely changed patterns, and the geometry is just totally warped.
Completely hallucinated.
Right. You are watching AI Paper Slop, the YouTube series, where we pull the most critical AI and tech papers, strip out the noise, and just give you the core insights straight away. And today, we're looking at a June 2026 release from researchers at Microsoft, Zhejiang University, Adelaide University, and Monash University. It's called Latent Spatial Memory for Video World Models.
And, the core breakthrough in this paper addresses that exact mutation problem. Historically, researchers have tried to solve this 3D amnesia by maintaining a persistent 3D point cloud of the generated world, but they do it in RGB pixel space.
Right.
This new paper introduces a system called Mirage, which completely bypasses the pixel space. It basically stores spatial memory directly inside the diffusion model's compressed latent space.
Which is huge. And the performance gains for, ML engineers are just staggering here. By cutting out the constant need to encode and decode images through a VAE, a variational autoencoder, at every single step, Mirage achieves up to a 10.57x end-to-end speedup.
It's massive.
Yeah, and it uses 55 times less GP memory. All of this while hitting state-of-the-art consistency on major benchmarks like World Score and Real Estate 10K. It is just a massive efficiency and quality leap.
Yeah, totally. And to truly appreciate why moving the memory into the latent space gives you that 10x speed up, we really have to look at the mechanics of what's been bottlenecking these video world models in the first place.
The root of the problem.
Right. The root of the 3D amnesia problem is the autoregressive context window. A standard video diffusion model only conditions its next generation on a really small temporal window.
Just the last few frames it rendered, right?
Exactly. Just those last few frames. It lacks a persistent global understanding of the room's overarching 3D geometry. So it's essentially just guessing the architecture of the room based on whatever happens to be in its immediate short-term memory.
Which is what led to the industry's previous standard fix, the RGB point cloud. To force the model to remember the room, systems would maintain this persistent, mapped-out 3D cloud of colored pixels.
Right.
So whenever the camera moved to a new angle, the system would calculate the new viewpoint, render a 2D image from that 3D colored point cloud, and then feed that rendered image back into the diffusion model to essentially say, hey, here's what this angle should look like.
But the fatal flaw in that whole pipeline is the translation step. The video diffusion backbone doesn't natively operate on standard RGB pixels. It operates on a compressed latent representation.
Yeah.
So to feed that rendered RGB image into the model, you have to push those millions of colored points through a really heavy VAE encoder every single time you need a conditioning signal.
Okay, let's unpack this with an analogy, because I love this. It's the equivalent of doing, complex data analysis using a Python script. But for every single step of the calculation, you force the script to print the data out on physical paper.
Well, that's a great way to put it.
Right. And then you scan it back in as a PDF, you run optical character recognition on the scan to extract the text, and then only then finally proceed with the math.
Yeah, exactly.
That entire translation process is what we call the pixel space detour, and it just utterly dominates the wall clock time during inference.
It really does. The computational waste is immense, but honestly, the loss of fidelity is arguably worse. Relying on an RGB point cloud is it's like taking a pristine 3D scan of a marble sculpture, painting it, and then trying to rebuild the internal structure of that sculpture using only the flat 2D photos you took of the paint job.
You just lose so much data.
You do. You're introducing rasterization artifacts and visibility holes. But most importantly, you throw away the rich, high-dimensional semantic features that the model natively understands.
Right, because a latent tensor inherently holds a deep representation of the scene.
Exactly. It knows about texture, it knows depth, it knows object boundaries. A 3-channel RGB pixel just holds a color value. That's it. So cramming a dense understanding of a 3D world through an RGB bottleneck, it just destroys the native intelligence the model has already built up.
So, since the pixel space detour is clearly the villain here, the Mirage system's solution is to keep the entire operation safely inside the latent manifold. Instead of storing colored points, Mirage constructs a latent spatial memory.
Yeah.
It takes the actual high-dimensional tensors output by the VAE encoder and pairs them directly with 3D world coordinates. But I have to ask about the actual mechanics here. How do we get these 2D latent cells into a 3D world space in the first place?
Yeah, that's the mechanical challenge, bridging a 2D feature grid into a 3D space. Because the VAE encoder just spits out a flat 2D grid of latent features, it inherently lacks any concept of, metric depth or z-axis geometry.
It's completely flat.
Right, so Mirage solves this during the initialization phase, using depth-guided back projection. It basically takes the very first initial frame of the video and encodes it into a latent tensor. But simultaneously, it passes that same initial frame through a standalone depth estimator.
And in this paper, they use depth anything 3, right?
Exactly. They use depth anything 3 to generate a dense pixel-level map of the metric depth.
Okay, so we have a high-resolution map telling us how far away every single pixel is, sitting right next to a lower-resolution map of the rich latent features. Because, like the VAE compresses the image, it has a spatial stride, meaning the latent grid is much smaller than the original pixel grid.
Yeah, and Mirage handles that discrepancy by downsampling the high-resolution depth map to perfectly match the smaller dimensions of the latent feature grid. It also rescales the camera intrinsics.
The mathematical parameters that define the focal length and optical center, right?
Yep, those exact parameters. It rescales them to match that new, smaller resolution. So using standard pinhole camera geometry, the system takes each individual latent cell, references the corresponding downsample depth value, and projects that latent feature outward into a 3D world space.
Oh, wow. So we end up with one latent attributed 3D point for every latent cell on the grid.
Precisely.
Meaning instead of a massive computationally heavy cloud of millions of colored pixels, we have a much sparser point cloud where every single point is a dense, semantically rich feature vector.
Which is vastly more efficient.
But that just establishes the memory, right? The actual generation process still needs to loop. Since we aren't rendering traditional images at every step anymore, the model needs a new way to, see this latent point cloud when the camera moves.
Right, and the engine that drives this generation without relying on constant VAE encoding is what the authors call the chunk-by-chunk cycle. It operates in 3 distinct phases: readout, injection, and update.
Okay, let's break down that readout phase first.
Yeah.
When the model needs to generate the next sequence or chunk of video from a new camera trajectory, it queries the 3D latent memory. It projects that 3D latent cache directly onto the target camera's 2D grid, and it does this entirely at the latent resolution.
Right.
But to handle occlusion, like where a foreground object blocked a background object, it uses Z-buffering.
And Z-buffering is a really crucial step to understand here. When you project a 3D cloud onto a flat 2D plane, multiple points might land on the exact same pixel coordinates.
They collide.
Exactly. The Z-buffer is essentially a depth array that tracks the Z-axis distance of every point. When 2 latent points compete for the same grid cell, the Z-buffer checks which point is physically closer to the camera and just discards the occluded one behind it.
Right, ensuring the model only sees the surface features of the geometry.
Exactly. So the readout phase gives us 2 vital outputs. First, we get a target view latent feature tensor. This tensor perfectly matches the native input space of the diffusion model, which is exactly why we don't need the VAE encoder anymore. Second, we get a binary visibility mask. If you move the camera to a completely novel angle, say, looking behind a sofa, there will be empty space on the projection grid where the point cloud simply has no data yet.
Because it hasn't seen it.
Right. So the visibility mask explicitly tells the denoising model, hey, this specific region is genuinely unseen. You have full permission to hallucinate new content here.
While simultaneously enforcing, this other region is known geometry. Use the latent features provided.
You got it. And once those outputs are generated, we move to the injection phase. These retrieved latent tensors are injected into the video diffusion backbone via a ControlNet style side branch.
And for those listening who might be less familiar with that specific architecture, a ControlNet side branch is basically a way to add spatial conditioning to a pre-trained diffusion model without destroying the model's underlying generative prior.
Super robust.
Yeah, it essentially acts as a highly influential geometric hint, guiding the denoising process to adhere strictly to the spatial memory without forcing the data through a rigid, lossy pixel representation.
Right. But if the model's only reading from the cache and injecting it via ControlNet, there has to be a moment where the system updates the memory with the newly hallucinated content.
Yeah, because after all, the end user still needs to see the video, which means you have to generate actual pixels at some point.
Exactly. If Mirage updates the cache, it must decode the latent features to RGB, estimate the depth of the new scene, re-encode those new pixels back into latents, and back project them into the 3D space.
But wait, doesn't that defeat the purpose if we have to do all that?
Well, that reconciliation step is where the incredible computational savings are actually realized. The decode, depth estimation, re-encode, and back projection cycle only happens once per chunk of frames.
Ah, okay.
It does not happen at every single conditioning step within the diffusion process. By batching the generation into chunks, Mirage completely amortizes the cost of the pixel space transition.
That makes total sense. You get the benefits of a persistent 3D world without paying the computational toll at every single frame. Here's where it gets really interesting, though. The concept of a persistent 3D cache anchoring geometry perfectly in place is brilliant for a static environment. Like if you're panning around an empty, rigid architectural visualization, it works flawlessly.
Sure.
But the real world is dynamic. People walk through rooms, cars drive down streets.
Yeah.
If we back project a moving car into our 3D latent cache, and then the camera pans away for, say, 5 seconds, the model shouldn't expect that car to be frozen in that exact location when it pans back.
Yeah, that would be bad.
Right. If we treat everything as rigid geometry, aren't we going to create a cache full of stale, ghostly dynamic content floating in midair?
This raises an important question, and that's the classic failure mode for persistent memory systems. If a system blindly trusts a static map of a moving world, it will hallucinate terribly. But Mirage addresses this directly with a dynamic object filtering step, and it's integrated right into the chunk update phase.
So the system has to somehow differentiate between what is a permanent wall and what is a temporary pedestrian before it updates the memory cache.
Exactly. And it relies on a combination of highly capable off-the-shelf vision models to do it. Specifically, during the update phase, Mirage runs SAM3 and Qwen3VL on the newly decoded frames.
Okay, so SAM3, the segment, anything model, is incredibly precise at drawing pixel-perfect boundaries around discrete objects.
Right.
But it doesn't necessarily know what those objects actually are.
No, it doesn't. And that's where Qwen3VL comes in. Being a powerful vision language model, it provides the semantic understanding. It looks at the segmented regions and identifies which ones represent moving entities like vehicles, humans, or animals.
Oh, that's smart.
It also identifies the sky, by the way, which has an infinite depth value and would severely distort any metric 3D projection.
Wow. So by combining the precise boundaries of SAM3 with the semantic intelligence of Qwen3VL, Mirage generates a highly accurate dynamic mask, meaning any latent cell that falls within the boundary of a pedestrian, a car, or the sky is explicitly denied entry into the 3D spatial memory cache. The moving objects are generated for the video viewer, obviously, but they are completely ignored by the persistent 3D map.
And the researchers ran ablation studies to prove the absolute necessity of this filtering step. When they disabled the dynamic mask and allowed moving objects to enter the cache, the long horizon generations became massively unstable.
Because of the ghosting.
Exactly. The stale dynamic content persisted in the spatial memory. So when the camera looped back around, the system would splat those latent features back into the new frames as bizarre hallucinatory artifacts. It completely broke the 3D photometric consistency that the model was designed to protect.
I mean, we have to acknowledge the trade-off here, which the authors do self-report as a fundamental limitation. Because the architecture explicitly excludes dynamic actors from the memory to preserve the rigid background geometry, Mirage fundamentally lacks the ability to maintain the state of moving entities across chunks.
Yeah, that is the catch.
Like, if a character wearing a highly specific red jacket walks off screen, the memory does not track them. When that character eventually walks back on screen, the model is forced to rely solely on its standard short-term autoregressive context window.
Right.
So the character might re-enter the frame wearing a blue jacket.
Exactly. For use cases heavily focused on highly dynamic scenes where complex moving actors are the primary subject rather than the rigid environment, this specific architecture offers fewer benefits. Mirage is unapologetically a solution designed to enforce rigid geometric consistency,
Yeah.
persisting dynamic content across long horizons in a way that respects physics, time, and object permanence that just remains a massive open challenge for the entire field of machine learning.
But, when evaluating Mirage for what it was explicitly built to do, stabilize environments, the benchmarks prove that ignoring dynamic objects actually solves a geometric drift on a long timeline.
The numbers don't lie.
On World Score, which specifically measures long horizon world generation quality, Mirage achieves the highest average score across the board. It outperforms incredibly strong 3D-aware RGB cache baselines like Spatia and Voyager.
Yeah, specifically dominating in the static partitions, measuring 3D geometry and photometric consistency.
Right. And we also see the success of this architecture reflected in Real Estate 10K, which is a data set heavily focused on novel view synthesis. The researchers tested closed-loop consistency, which, that is a brutal evaluation metric.
Oh, it's so hard.
You force the model to generate a very long, complex camera trajectory that wanders through an environment and eventually returns to the exact starting viewpoint. Any microscopic inaccuracy in the geometry at any individual step accumulates exponentially.
Yeah, if your system suffers from drift, returning to the start will yield an image that looks completely foreign.
Completely. And Mirage hits state-of-the-art closed-loop consistency metrics on this dataset, proving conclusively that maintaining a latent spatial memory prevents long-term geometric degradation.
It's phenomenal. And exploring the engineering choices behind those benchmark victories reveals some really fascinating nuance. There is one highly specific mathematical choice in the paper regarding downsampling that highlights how easily a state-of-the-art model can break.
Oh, the interpolation stuff.
Yeah. When Mirage builds the memory cache, it has a high-resolution metric depth map from depth anything 3, and it must compress that map to match the lower-resolution latent feature grid. The exact mathematical interpolation method used for that downsampling dramatically impacts the entire system's viability.
Coordinate space translations are just the silent killers in machine learning engineering.
They really are. The paper tested several standard methods. Like if you use nearest neighbor downsampling, the algorithm simply looks at the closest high-resolution pixel and adopts its depth value.
Which preserves the sharp, distinct edges of foreground objects, but it introduces terrible aliasing and jagged artifacts.
Right. And if you use area pooling, where the algorithm calculates the average depth of all the pixels in a given area, you end up over-smoothing the data.
Right. The distinct boundary between a foreground chair and a background wall just gets blurred.
Exactly. The foreground geometry physically bleeds into the background at the occluding contours, creating these warped, melted-looking objects in the 3D cache.
So what did they use?
The paper empirically found that bilinear interpolation was the mathematical sweet spot. Bilinear interpolation looks at the 4 closest pixel centers and computes a smooth, weighted average based on distance. The researchers measured the success of these methods by calculating what they call the hole rate.
Right, because when you project the 3D cache back onto a new 2D target view during the readout phase, the hole rate is the percentage of empty latent cells on that projection grid.
Exactly. And bilinear interpolation yielded the lowest hole rate by far at 42.53%. It provided the most continuous, reliable coverage for the projected cache without hallucinating phantom geometry or melting the edges of objects.
It is just a brilliant reminder that simply throwing massive compute at a problem doesn't work if your foundational spatial math is lossy.
No, you have to get the math right.
But beyond the math, the most profound insight in this paper, for me at least, comes from visualizing what is actually stored inside that memory cache. Because Mirage stores VAE latent tokens instead of RGB colors, you can't just look at the point cloud on a monitor.
No, it's gibberish to the human eye.
Right. Every single point is a massive multidimensional tensor representing abstract features. So to understand what the model was actually memorizing, the researchers ran principal component analysis, or PCA, on those latent memory tokens.
And PCA is a dimensionality reduction technique. It takes a massive tensor, say 64 dimensions of abstract data, and mathematically isolates the top 3 axes of greatest variance.
So they took those top 3 principal components and mapped them directly to red, green, and blue values so they could visualize the data on a screen.
Exactly. And the results are incredible. When you look at a standard RGB point cloud, a pixel on a table is just brown. It has absolutely no idea that it belongs to a table. But when you look at the PCA visualization of Mirage's latent memory, the entire table lights up in one uniform, coherent color. The walls map to an entirely different color. The floors map to a third.
It's so cool.
The visualization proves that the spatial memory isn't just visual, it is deeply semantic. The tensor inherently knows where the boundaries of the table end and the floor begins without any explicit human supervision.
The latent memory literally holds an understanding of what the object is, encompassing both semantic category and textural structure.
Right.
And that is exactly why the diffusion model can generate such stable, high-fidelity views when it queries the memory. It isn't just receiving a colored pixel constraint saying, put brown here. It is receiving a dense semantic hint saying, this specific region is a continuous wooden coffee table.
Exactly. And it allows us to scale world-consistent generation efficiently. But the semantic nature of those latent tokens opens up a much larger, frankly, mind-bending possibility.
Oh, I know where you're going with this.
Yeah, if these latent spatial memories inherently contain deep semantic and textural information about discrete objects in a 3D environment, the logical next step is directly editing the latent point cloud.
Right. We aren't just locking the geometry. We could manipulate it.
Precisely. If the cache fundamentally understands the concept of a wooden floor in its latent representation, we could perform text-to-3D semantic edits directly on the memory structure.
Wow.
You could prompt the system to swap the concept of a wooden floor to a marble floor simply by tweaking the underlying latent tokens in the 3D cache.
Because the memory dictates the generation, you could theoretically watch the entire generated video timeline update seamlessly in real time, reflecting the new marble floor from every single camera angle.
Completely seamlessly. By moving the memory into the latent space, this paper lays the foundation for a completely new paradigm of direct 3D video editing.
That is just wild. The ultimate takeaway for anyone tuning into this deep dive today is that the future of video world models lies entirely in the latent manifold. The pixel space detour was a computational crutch.
Yep, it's obsolete.
By eliminating the need to render and encode images at every step, the Mirage system solves the memory bottleneck while completely preserving the rich, native semantic features that the generative model actually requires. We have spent years trying to figure out how to take better 2D photos of the 3D world to feed back into these models.
And now we don't have to.
Now we're realizing we can just reach directly into the latent space and rearrange the concepts ourselves. Thank you for joining us for this analysis on AI Paperslap. Keep reading, keep building, and we'll see you in the next one.